This is the very famous NE555 chip, and this is a simplified model of its internal structure. In this video, we'll dive into how the NE555 works and how to analyze a circuit. This is a PWM circuit built with the NE555 to control a bulb's brightness. The circuit looks a bit complex, but once we understand each key part, analyzing it becomes easy. First, let's look at how each important part inside the NE555 works. Here are three precise 5K resistors in series between pin 1 and pin 8, forming a voltage divider. Pin 1 is the negative supply, and pin 8 is the positive supply. This divider gives us two exact voltages, 2/3 VC and 1/3 VC. With a 12-volt supply that becomes exactly 8 volts and 4 volts, these voltages go into the non-inverting and inverting inputs of two converters. What's a comparator? It's simple, it has two inputs and one output. The plus sign is the non-inverting input, and the minus sign is the inverting input. And the bottom pin is the output. If the non-inverting input is higher, it outputs a high level. If the inverting input is higher, it outputs a low level. The other inputs of the comparators are connected to pins 2 and 6, so the voltages on pins 2 and 6 control their outputs. Their outputs go into an RS flip-flop, which also has two inputs and one output. Every flip-flop has a truth table, and here is the RS truth table. You don't need to memorize it, just look it up when you need it. The table shows output Q, but inside the NE555, the output is Q bar. We all know Q bar is simply the opposite of Q. Here's the key point. What hold means in the truth table? If S is low and R is high, Q bar outputs a high level. If both go low afterward, the output stays the same, still high. Q bar drives the base of an NPN transistor. This transistor acts like a switch. When the base is high, the collector and emitter conduct. That means pin 7 is pulled to ground when Q bar is high, making it the discharge pin. Q bar also goes through an inverter to pin 3. The inverter flips Q bar again and outputs it on pin 3. So pin 3 is the output pin. There's also another input to the flip-flop connected to pin 4. This is the enable pin. Pin 4 must be high for the flip-flop to work. That explains 7 pins. Pin 5 is the control voltage pin, and it's rarely used, so we'll skip it. With this structure, we can build a truth table for the pin states. This table will make analyzing the whole circuit much easier. Now that we understand the inside, let's look at the external circuit. This is a 50K potentiometer. Turning the knob changes the resistance between either end, and the wiper. To make it clear, we'll monitor its resistance with 2 meters. Both meters show 25K now. Their sum equals the total 50K. Turn it counterclockwise, the left value decreases and the right increases. The sum is still 50K. Keep turning it all the way. Now the left side is 0 and the right is 50K. Turn it clockwise, the left increases and the right decreases. This potentiometer controls the charging and discharging speed of the capacitor. Here's the capacitor, which stores electrical energy. If we connect it directly to a power source, its voltage rises quickly. Adding a resistor slows the charging, and a larger resistor slows it even more. Alright, now we understand all the key parts. So understanding the whole circuit will now be much easier. Pin 3 goes to the MOSFET gate, controlling the bulb. Of course, the switching is very fast. At hundreds or thousands of hertz, the blinking is invisible. We control brightness by adjusting the ratio of high and low time in each cycle. More high time means higher average voltage. Less high time means lower voltage. The average voltage sets the brightness. Higher average voltage makes it brighter, lower makes it dimmer. This method is called pulse width modulation, or PWM. Pins 1 and 8 are power pins, ground and VC. Pins 2 and 6 go to the converter inputs. Here they're tied together and connected to the capacitor. Current charges the capacitor through a resistor, a diode, and the potentiometer, and discharges through the pot, the other diode, and pin 7. Pin 4 enables the flip-flop, so we tie it high. Pin 5 isn't used here. We connect it to ground with a capacitor and slow the circuit for easier viewing. When power is applied, current charges the capacitor. The capacitor voltage rises from 0 because it's tied to pins 2 and 6. As we said, they go to the inverting and non-inverting converter inputs. Right now the capacitor voltage is below 1/3 VC. According to our table, pin 2 1/3 VC, pin 6 2/3 VCC. So pin 3 outputs high, and the bulb lights up. As the voltage passes 1/3 VC, pin 2 1/3 VC, pin 6 2/3 VC, the output stays high. The voltage continues rising until it goes above 2/3 VC, now pin 2 1/3 VC and pin 6 2/3 VC. The table says pin 3 goes low, so the bulb turns off. Notice, Q bar is now high. So the internal transistor's base is high. The transistor conducts, pulling pin 7 to ground. The capacitor now discharges and its voltage drops. According to the table, pin 2 1/3 VC, pin 6 2/3 VCC. In this range, pin 3 stays low. When the voltage falls below 1/3 VC, pin 3 goes high again. Q bar becomes low, the transistor turns off, pin 7 stops discharging, and the capacitor charges again. At this moment, the circuit is back to the initial state. This repeats, producing a stable square wave. At normal speed, the output frequency is about 1 kHz. The bulb flicker is invisible. Now you can see the potentiometer simply adjusts the charge and discharge time. Turn it counterclockwise, charging is faster, discharging slower, duty cycle decreases, bulb gets dimmer. Turn it clockwise, charging slows, discharging speeds up, duty cycle increases, bulb gets brighter. Alright, that's the end of this video. Thanks for watching.